Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. It's 2020. Don't I sound excited? And the first thing in my chat is Kappa. Typical. Howdy guys in the chat. Dark Second, Dana Collin, Zokwar, and Twinzen? Wistertobe, how's it going? I hate that the chat is on the other side now. I still have not configured any of this stream stuff. Oh, okay. I moved the activity feed, but not the chat. Don't worry, I'll get this figured out. I am not used to this new Twitch UI at all. And I spent 0 time to fix that. Hey, Two Curbs. Hey, Coach Otter. So this episode I called kaze, and kaze is the Japanese word for wind, and I think I've mentioned this a couple times before. But what it essentially is, it was a Python file for a while in the repo. But what it is my own HDL, and the reason I wanted that, well, there's a lot of reasons, but essentially the mental model that I have when I'm using, I'm so brain dead today. I just need to be straighter about it. I don't like Verilog. And the reasons I don't like it aren't so much like syntactic. I don't really care about that. It's mostly that it doesn't at all match the mental model that I have of working with hardware. And there are a lot of smaller things, like I also don't really like using Verilator, even though it's an awesome tool. It's if you're using Verilog and you're doing a lot of your testing or want to do a lot of your testing in C or C++, it's the tool. It's really good. But at some point I was just like, you know what, screw it. I'm going to try to make my own HDL. I kind of know what I want it to look like after a bunch of years. And so I did that this last summer. I started like prototyping it in Rust and wasn't that happy with the API that I came up with, and then ended up doing it in Python, and then ported a bunch of the XenoWing code over to that. And I was a lot happier writing code with that rather than Verilog or even System Verilog, which is what I was using. And it was fairly easy also to get that going. And then I decided at some point that when I was working on the rasterizer that I had set up, where it was purely a software model, I got, in particular, the rasterization part of it to be its own module in software, and figured out how it was going to work and put everything together. And then as it sort of came time to port that over to actual logic code and hooking up a simulator, what I basically wanted to do was keep the software model with everything else, because it has the entire rest of the pipeline, of a 3D pipeline. I would like to just swap out the rasterizer in software with a software model that does the same thing. So I could either go through all the trouble of setting up Verilator for that. But the more I thought about it, the more I thought, well, I'm using my own HDL anyway. What I should do is lean into that even further and make it generate not only Verilog, but also simulator code that can be Rust code. So essentially, it just does the same thing that Verilator does. But because my HDL is, at least in my head, simpler, it shouldn't take that much effort to make a simulator. And I'm right about that, it turns out. So we're going to talk about that. So I decided before I would have it to start generating Rust code, since the original was written in Python, I thought, okay, let's take the opportunity to port the HDL to Rust. And while I'm doing that, I'm going to document it and test it. And so that's what I've been doing, especially over Christmas. And I think it's going pretty well. I can show you guys how far I am with that. Yeah. But actually, before I do that, I'll just show you some of the test code, because maybe that actually makes the most sense. So what I've done here, this is actually kind of cool. So I made the library in sort of 2 parts. By the way, all of this is published, or it's not published on crates, not until it works. But it's all on GitHub. I'll post the repo here. And the idea is that there are two projects in here. There's kaze, which is the HDL itself, and really this is like, I kind of call it the compiler, because I'm sort of treating this as an HDL, but really it's a Rust library. And we'll get into some of the design ideas behind kind of trying to like make this so that you use it as if it were a programming language, even though it's an embedded language. But yeah, so I have kaze, which is the compiler itself, and then there's kaze sim tests. And the reason I have that as separate is so that I can have the kaze crate only care about being able to create like a module, and then have facilities to output a simulator, output Verilog from that. So it's all the code generation and all of the module graph and everything that you have is all in that one crate. And then in order to test the simulator, I have another crate that just pulls that in as a dependency, which is here. And in fact, here it's actually a build dependency, because then we use the build.rs script in here to output a file. And in that file, we call sim generate on all these different modules that we make. And then in lib, we include that file, which is modules.rs, which looks like this. And then these are our simulators. And then in lib.rs, after we've included this in this modules thing, then we can actually run through and do some unit tests on them as well. So with this, I have kind of a full end-to-end thing where I have the kaze crate, which again has a way to actually create modules, and also a way to generate, for example, simulator code for the modules. I haven't actually ported over the Verilog generation because I'm not really going to change it from the Python thing. And I figured let's make the API work and make it work with the simulator first, because that's kind of the new part, and get that going. And then I'll just port over the Verilog stuff, which I don't think will be very difficult. And I also came up with a really nice way to do code gen for the simulator. So I'm really happy with that. So I'll probably reuse some of those ideas when I port over the Verilog stuff. I'm not entirely sure how I'm going to test that yet either. I'll probably actually lean on one of these other crates that people have made to do a lot of the like bootstrapping for you of like getting Verilator stuff into Rust. Yeah, I'm not entirely sure how I want to do that yet, but maybe I'll come up with a good way. And when I come up with a good way to test it, then it makes a lot of sense to try and reuse some of these tests maybe. Maybe it's possible for me to write these same ones in a different way that's actually agnostic of what this simulator thing looks like. Maybe I can even generate like a tester that would expect the same module to exist in Verilator elsewhere, and then goes and instantiates that and tests it. I don't know. I'll think of something. But this totally works so far, at least with the API that I have right now. And I'll do this. I'll just do cargo doc node deps in open, because that's probably actually one of the easier ways to show the API. So there's a lot of to-dos in the actual documentation, which I need to fix. But most of the important things are there, except I want to have like a nice introduction for why I'm doing this and what it's going to be about. And then I think in this module, it's a module called module, which kind of sucks. I might change that, but this is for creating a module, and a module in Kaze or Verilog is like a class, but for hardware. So it's one reusable component, or sort of like a blueprint for a reusable component. Then you can instantiate. Instantiation is actually not something that I've done yet, but I have in my head how it's going to work. So I'll figure that out later. But here is actually where I want to have most of the meat of like how you can use this, or maybe that goes in the main one. I'm not entirely sure. But then the idea, and I can show you this with the tests as well, in build.rs. So a really basic example is just something like this. So what we do is we create a context, and here I just do context new and then use that context for all of them. And the reason why you need a context is you need something to hold, to own all of the objects in this graph. So the idea is that you create a graph which contains one or more modules, and then you do code generation for one of the modules. That's kind of the idea of this. And in Verilog, it will generate all the modules that depends on everything. And for Rust, it will, basically do the same thing, but it will, generates code a bit differently, because in Verilog, we can take the module concept and basically just generate Verilog code that's almost identical to the modules that we create, and then in the simulator, I actually flatten all of those, or at least that's the plan, into one larger thing, because that makes the code gen a bit easier in that case, and it makes the evaluation of the propagation of the signals easier. And all that I'll probably write about in the documentation here, but anyway, that's the idea. So you create a context that kind of owns everything, and then from a context you can create different modules. And when you create a module, then you have this module, and then you can do things like, I'm going to add an output called O in this case, and I'm going to sync that with this input signal, which is called I, and it has 27 bits. So this, hi Finrog, thanks again for the sub. He's joking about the JavaScript. He knows it's all hell. So yes, these are some really basic modules here where I just literally create an output that I just sync with an input. And these are both the same thing, but then different bit widths. And there's also things like bit and, so you can make two inputs and then and them together with this and operator, and you can do the same with or. I need to have exclusive or here as well. You can basically do that with not, and you can do not with wider signals. In fact, this is 4 bits wide, for example. And then you can make registers as well. So here I create a 32-bit register with no default value. And then I'm going to drive its next value with another input here, and then I output that. And the reason why I have drive next with as like a separate function here is because for these simpler examples, you can't actually create feedback in the graph, because these are all like combinational logic that you've described here. And the only loops that are actually allowed in this HDL, there's no combinational loops allowed, I've decided. And the only way you can make loops is through a register. And so that's why this needs to be separate. And this also allows you to, for example, create a register and then drive it with itself, which is something you would often do. So that's kind of what that's about. And then eventually you can output that. In this case, we're going to output the value of this register in an output called O. And then what this gets generated into, like for the simulator, for example, we can show these same things. So you get a struct, and this struct implements default, which right now I just use for not having to generate like a constructor. And in this case, these really basic ones are purely combinational. So they only have inputs and outputs, which are a certain type. And essentially what we do is we take the amount of bits that signal has, and then we round it up to the next nearest power of 2 data type. And then there's this one function that's on these that we call prop, which is for propagate the signals. And actually, I can probably remove this unused parens thing now that I generate the code and I generate a bunch of intermediates like this. Maybe I'll get rid of that. Anyway, there's this propagate, which will propagate the signals. So the idea is that you set the inputs to some known values, and then you call this propagate, and then the outputs should reflect the inputs and the logic that you described. So in this case, the only thing that happens in this really basic case, this was up here where we just had an input that was 27 bits wide. And all that happens then in this test, or in this generated code here, is it takes the input and then it masks off the other bits other than or essentially includes these lower 27 bits and then sets the output to that. So so you get this 27-bit restriction kind of enforced by the module here. And then for the next example, it was also it was basically the same thing, but we had a 128-bit signal, which can be directly described by this U128 type in Rust. And there, no masking is required because it's already the same amount of bits as the output. So there it just generates this code. And then for example, bitwise and bitwise or, it does what you'd expect here. And these are 1-bit signals, so these actually get generated as booleans. I think the four types that I end up supporting are bool U32, U64, and U128. And so actually right now the simulator has a restriction that you can only have signals up to 128 bits, which I think I documented that might be lifted eventually. So for example, if you have a module or like this, when you create a literal, if you create something like that, then it'll say panics if this bit width is less than min signal bit width, which is 1, and then or greater than max signal bit width, which is currently 128. But I mean, I might support wider than that in the future if I ever actually need it, but for now it's a lot easier to not have And then when we get down to like registers, like this one, then the registers are kind of interesting. So as soon as we have a module that uses a register, in addition to this prop function, we also get a reset function and a function to trigger a positive edge of the clock. So the other thing is that clocks and resets in this language are not ever described anywhere. The idea is that the resets should be kind of implemented by, like, you should use a consistent reset strategy, and that should be kind of an explicit thing. That you shouldn't be combining with your combinational signals. That's kind of another thing that I'm imposing in this language. So you can see it's kind of fairly limited, but it's the limits that I want to impose that make my life easier on my project. So it kind of makes sense. And I think actually this subset is the kind of things that you generally do for most of your logic anyway. Or maybe I'm wrong, but then you can use someone else's library. So then in addition to getting this prop function, which again just does the same kind of propagation that you had before, you also have the reset, which will then put all the registers, their current values, into whatever their default values was. In this case, I think the original module had no default value specified, so it just got 0 in this case. And then when you do propagate, it propagates signals from the output. Oh yeah, another thing. The structure also gets some storage for the current register value and also the next value for all the registers. And so what happens is when you reset, that gets set to this value, whatever the reset value is. And then when the clock ticks, this gets set to whatever its next value was. And so then what propagate does is it propagates all the signals to all of the outputs and to all of the next register values. So in the cogen, we kind of just treat the outputs and then the next register values as the two things that we go and figure out what they need to be, and then we propagate those signals. So in this case, if you had the usage of this, if we go down to one of these register modules, in this case, you create a module, and I might change the API that when you do default or new, you get the reset state. I'm not entirely sure about that. But the idea is then what you do is you set the input and then you propagate. And then this won't like tick a clock. This will just propagate the inputs into the module. And then you would normally tick the clock and then it would propagate out from the registers. So that kind of makes sense. Yeah, I'm really curious about that as well, DarkSecond. I obviously haven't done any tests about that, but I'd expect it would actually be quite fast because if you don't allow any combinational loops and you flatten the whole graph, then all of your signal flows one way, which means you don't have to do like these event-driven systems at all. It just gets all pretty straight line code. But Verilator also, I think, recently added a bunch of multi-threaded support, which we're not doing here at all. So I think at this point, the latest Verilator would probably win. But that's something I could make a more sophisticated simulator for if I wanted to. Yeah, so I have some other examples here where I just have more registers driving each other and then testing that a signal propagates through there with a certain delay. But it's the same idea, and you get the same kind of code generated. So in this case, each register gets its own storage, and its next value also gets storage. And then propagates to all the registers and all the outputs, and then the clock ticks all the registers, and resets all the registers. And that pretty much covers like the whole language, really. I've pretty much there's really nothing in this API or this language that is more complicated than this. Instantiations will get slightly more complicated, but they will still compile to the same kind of simulator. It's just the only real difference is that everything's going to be flattened into one graph before this happens, and then we need to also because I have this sort of inherent restriction with a lot of these basic operators. So when you create an AND like this, it's essentially going to create an AND gate, but you need both of the inputs to be able to call this operator. So you have this implicit restriction that you can't create an output without all of the inputs available. And this is actually really nice because this allows you to, or this actually enforces the restriction that you can't have loops in the combinational chain. But at a module level, that kind of breaks down. I think this is generally okay at this level, but like within a module. But external to a module, that doesn't work because you often have signals that come in and out, and some stuff might depend on some other things. So within a module, I think that's safe. But then outside of a module, we need to be able to instantiate a module and then hook it up because some things might be outputs that then we need to have in order to create some logic that then we're going to feed back into that module somehow. So globally, it's still after we still need to enforce that there's no loops that are formed by those structures, which is one of the reasons why I've deferred actually doing module instantiation in this implementation so far. But I think that that's actually relatively easily enforceable. So I'm not too worried about it. And then I think the simulator code just looks exactly the same. So yeah, that should just work out. And then you have a bunch of like combinators, which is where stuff gets fairly useful. So not only can you create simple modules and create registers, but you can also do things like, here I have an input, and this input is 4 bits wide, and then I can use this. No, my preview just froze, but not my stream. So you create this input that's 4 bits wide, and then you can call this bit function, which gives you a new signal that represents, for example, bit 0 of this signal. And you can do things like bit 2 dot bit 0, because bit 2 will give you a 1-bit signal, and then of course you can take bit 0 from that signal, and you can chain all these. These combinators where things actually get fairly useful. And of course this just represents what you have in Verilog, where you have I 0. Or you can do bits as well, which is you get a range of bits. So in this case, this would be the same as in Verilog, as I 2 down to 0. Stuff like that. I might even actually add some syntax to do that. So we'll see, but probably not. And then one of the nice things is that whenever you call one of these functions, this will actually make sure that this input actually has enough bits to satisfy that requirement. And one of the things about this library that I really debated in my head is that I've decided that most of the error handling is actually just going to be with panics. And that means you can't catch it. But the reason I chose that is because in some of these simpler cases where you just apply these basic operators, there's no way to make these, or at least no very ergonomic way to make these return options or results. You'd have to, I think, wrap everything like this, which really sucks when you start combining these. So that's not something you want to do. Though, I actually just realized, thinking about it now, that it might be possible to make those chain by using operator overloading. And being able to accept, for example, a result of this rather than this, as long as it's the same error type. And maybe that actually works. But then, even if that were the case, what we would gain is the ability to catch errors that are generated by using this API as a language. And we would end up seeing these errors sometime later, unless we took one of those like error, whatever those crates are. They're supposed to make error propagation easier, that will actually do stack unwinding for us. Because actually, if you were to do this in HDL and you did something bad, you would actually want this to break on this line. And so I actually decided that panics actually give you that experience almost. At least you can enable backtrace, and then that will give you the line in here, and that it fails. Then the next line gives you the this line, which is actually what we want. So I've decided, for ergonomics and actually usefulness of this as an HDL, that this module API will handle errors with panics. So I'm still not in love with that, but I think it's the best choice. And anyway, that makes this nice to use, because then it will always check these as you build the graph, and it will error as soon as there's something that it can detect that's wrong, which is nice. There are a couple things it can't detect right away. One of them being if you have a register that then you don't drive its input, that's an error, and that isn't checked until we can do code gen, because that's when the graph's actually traversed. Things like when we have module instantiation, checking for combinational loops, that has to be deferred as well. So it might also be that one of the things that I've been considering is doing like this, where we turn all of these into macros, and the only thing that they would add is additional arguments that would contain the file and line of these, and then we're able to, for those error cases that we can't throw on right away, at least we'll get source information for reporting that later. So that might actually make some sense, but I'm not sure. Anyway, you can do other things like repeat. So if you have a certain signal, like this is a 4-bit signal, we can repeat it once. That, of course, represents the same thing, but we could repeat it twice, and then we get the same signal repeated twice. You can see in the tests for this, essentially what that does. Yeah, so here we have this input, which we set to 0xa, and then repeat 1 was this, repeat 2 was this, repeat 5 was this. So lots of different bit widths and stuff. And you can see also as we widen between data types or between these different widths, the code generator handles that correctly, which is nice. And then you can also do things like take the 0 bit and then repeat that a bunch of times. So I did that as well. You can also concatenate two signals together. So you can take also have these convenience low and high on the modules. You can just get a 1-bit signal that's 0 and 1 bit that's 1. Easier than writing a literal. And then concatenate that with some input, which does basically what you'd expect. And then you can also do this mux. And so one of the things I've also been playing with, and this is something that, one of the reasons I haven't published this because it's not documented or not everything's implemented. But one of the things I wanted is with this kind of API, one of the things that you do lose is the ability to have this kind of if syntax, which is actually something that's really nice in Verilog. So I would like to support this somehow, and I think the way that I'm going to do that is similar to what I did in Python, which is you sort of break into this syntactic sugar, and then in here you basically only have if statements and assignments. And the idea is that it will convert all of these assignments that are in if statements to assignments where these are basically conditional. So instead of I equals not I, for example, in here, then what this will actually do is it will write the code I is I dot mux, and then it will select not I based on not m dot low, for example. Or I think, yeah, it would write out something like that. And then this, of course, would also be an input. This same transformation would happen here as well. So it would kind of put all that together for you, which I think is really nice. And then I might also look into that for other constructs rather than just if. For example, a switch case thing might be really nice. And especially with procedural macros, I think this could be really nice to implement, and we could produce a lot of really helpful errors that don't just explode the macro system. So I haven't entirely worked out all the kinks about this, but I know that this is possible to make work nicely because I made it work in Python with hacking some C Python specific stuff where I just modified the scope, the color scope, which is not something you're supposed to do, but it was a good prototype for how this could work. So that I think is kind of an important thing to have in this kind of language, because most of the time I think that working at almost a netlist kind of level like this is actually at least what I want to do in my head. But then sometimes you also really want to be able to especially have multiple signals that are in here that are all, you do a different thing based on some conditional here. And then you essentially want to have ternary expressions based on this conditional for all of these different ones. And this is a really natural way to write that. But at the same time, this also is still more consistent than something like Verilog, because the only way to do this is this, and this is only syntactic sugar that is very clear about composing combinational only signals still. And then to write these to registers, you have to actually hook that up explicitly. So I kind of like that. Maybe it's a bit verbose, but I think it's nice. But I also need to figure out the rest of the details. So that's why this is all in just this build script. That's where I just have it now. But I think what I would do is have this either in the kaze library itself, or if it's a procedural macro, I'd probably actually put it in a separate crate. I guess it probably can live in the same one. I'm not actually sure. But I kind of like the idea of having the syntactic sugar stuff in a separate crate where you can kind of opt into that, or at least as a feature maybe. Which Rust packages allow you to do. So even though this module API for building the modules is, we'll just panic whenever there's something that's wrong, which I think is, again, fine, because as a user of this library, I think that's what you actually want. The rest of the API, for example, the simulators will actually propagate errors more properly, and I think that's fine. Right now, though, of course, they don't really generate many errors. In fact, I think I have a panic in here, actually, in the simulator. No, I don't. Well, I think there's a couple errors, because you can have IO errors, and then there's another kind of error as well in here, I think, which is the undriven registers. Oh, no, it's expect here, yeah. So this needs to be turned into a proper error and tested, but anyway. Especially things like IO errors, you want to propagate in the normal way. So the rest of the library will just propagate stuff. But that's really all there is in this library. There's the module API, which is where all the docs are and all the interesting stuff is. because this is where you create modules by composing signals and registers. By the way, hi Alkama. Did I not say that? Sorry about that if I didn't. And hi Crossbow. So the thing is, you would compose modules by composing signals and instantiations and everything, and then after that you would either generate some simulator code or generate some Verilog code or both. And this, of course, this is all just dumping code into writers, so it's as composable as it can be as Rust code. So the simulator module, I think the only public function that it actually exposes is called generate. Which is here. You can see it takes a writer. In fact, it takes a mutable reference to a writer. I might change that. There were some Rust guidelines I read about where I guess this is not the right pattern, but I'll fix that. And then a reference to a module, and it will generate, it'll just dump the output into that writer. And that's, of course, quite nice because then it makes it easy to, for example, here in this test for the simulator generator, I only have to do all this file stuff once, and then I can just dump everything else out to that same file. Or however else you want to do this. It doesn't really matter. But this was one way that you could do this. So the idea then is one of the ways I'm going to integrate this into my project is once I start working on the rasterizer, which is going to be implemented in this language, I'm going to do exactly this, where I'm going to have probably the rasterizer as its own crate. And then I'm going to make that crate a build dependency of the project that now I'm testing the rasterizer in. And so in the build script of the rasterizer project, I'm going to do all this stuff where I make a context and dump the module from its own crate into a file. So that crate will only export one function, and it's going to have one dependency, which is this library. And it's going to export one function, which is generate this module in a given context. And then I would literally just call that and then call this sim function around that to dump that into a file after putting in this context. And there might be other modules that depends on, so it would need to generate those also into the same context. So you would give it a context, and it would generate all this stuff, and then you dump all that to a file. And then in the rasterizer, instead of instantiating my Rust object, so I can show you that actually. Here I have this color thrust is what I called it. So instead of instantiating this struct, I instantiate my generated one, and of course. Most of the registers here, I've also just made these public fields here, which I did thinking ahead, knowing that I was going to have that same kind of interface for the simulator. So I would do that instead, and then that's basically it. Although probably one of the other things I'm going to do is I might actually make a trait for this color thrust thing, and then have two different implementations, one that uses the software model and then one that uses the generated simulator. Maybe, we'll see, because there's a lot of extra plumbing there that I might not want to do. But it'd be nice to keep those still kind of hot swappable to as much of a degree as they can. And the other thing that's nice about having these modules as their own crates is that they can also export other things, like if they have a bunch of constants, like this does right now. It's useful to have these available to whatever software is going to interact with these, because you need to know how wide some of these interfaces are, or how many fractional bits some of these parameters have when you're doing the, in this case, triangle preparation for this unit. You want to have these constants elsewhere. So then what's really nice about that is that none of this hardware code is separated from Rust, which is kind of where I want to actually do most of the testing. So I'm really excited about this approach. It might seem like overkill to do a simulator in HDL like this, but I did the HDL for fun, and now I like using it. And then once I'm already doing that, I might as well do the simulator stuff for it too. That then brings the code directly into Rust in a way that it's already composable. Because again, these generated modules, they're just structs. There's nothing magical here. There's zero extra code about logging or tracing or anything, which that might actually change. It'd be really nice to give these the ability to give trace output, or at least optionally give trace output, that we could then look at in GTK wave or whatever, some kind of waveform viewer. But we'll see. I think actually, for the most part, having this stuff available as a software model that's this accessible is probably going to be enough, but we'll see. And of course, sometimes it's possible to make the code generator kind of blow up like this, but it actually blows up linearly, which is the nice part. Like in this case, I described that I want to repeat a bunch of bits, so it does that the right way. The initial implementation of the simulator, this is actually the second implementation I did. The initial one would expand at least quadratically, so this is quite a lot better. But it's pretty simple to generate that kind of model, as you might expect. You basically just trace from the outputs or from the inputs to the registers, which you could kind of consider other outputs, and you make these expressions that are just assignments. And then of course sometimes when you make an assignment expression, you might make stuff that it depends on. So for example, in this case, we're going to assign it to a node that represented this input. And then we compile that to a reference to a temporary expression that we also emit. And then that, of course, is the input itself with this binary operator and this constant. So the compiler itself for doing that, like there's this compiler object in the simulator module here that just does that. So for example, input is literally this. We figure out what the target type is going to be. And then we get, for this expression, we make a reference to this member, which is going to be the actual input. And then we generate a bitwise mask in case the output of this is actually not as wide as that input. And then of course, gen mask here will only do that conditionally. So it's pretty nice. So I really like how a lot of this code ended up. It's really straightforward. And the API itself is really easy to make, actually. But so far I'm happy with it. And again, I'm putting in some nice effort to document this, both for myself, but I do want to actually publish this as something I hope to maintain for a while, because I think it'd be quite nice to, I think I'm going to end up doing a lot of hardware projects, not just the Xenowing. So it'd be nice to just play with that kind of stuff in an API that's natural for me. And if that's what this ends up being, then that's great. One of the things, though, that this totally has not addressed at all as an API is any sort of like higher level type safety or collections of signals. So if you want to like describe an interface, or if you want to have some kind of type checking on the types of these interfaces, right now these signals are just kind of bags of bits. But I think that can be done on like the next level up, the next abstraction layer. So for example, you could have a kaze int 32, which would internally just have a reference to a signal that has a bit width of 32. And then you could define operators on those, including operators on like literals that would compose with some other things. And then I think it would be fairly natural to implement that if that were required. And you would still get all this lower level checking. All the simulator stuff would just work the same way. So I think it's not the right solution to solve that at this level, actually. That's pretty nice. Anyway, I think this will be good. And I thought what I wanted to do today was just talk about all that, which I've now done for 45 minutes or something. Maybe not that long. I started pretty late. And then start to just implement some of the missing features right now, because I made this ticket on GitHub, which I just closed. No, I have it open already here. Where this is just the things that I haven't done yet, because the initial plan was just take exactly what I have in Python and just move everything over, and then eventually replace all the usages of the Python stuff with Rust code, which should be straightforward because I'm not really changing the API design other than to the problems I've had to solve to make it more Rust-like. And then just actually, I lost my train of thought mid-sentence. It's one of those days. But yeah, so I think I just want to implement the rest of this to sort of reach feature parity and then do some other stuff. Now, of course, some of the things I'm still not sure about is that like if syntactic sugar. I'm not that familiar with writing macros in Rust, and it's kind of a difficult thing to do well, I've found. But so this one might take me a while, but like the Verilog gen, I don't care to even start right now because I just know it'll be relatively straightforward. And I also kind of want to do something that's somewhat interesting as a test for this when I actually start generating the Verilog that might even be separate from the Xenowing, just to kind of put it through its paces before we even get to the rasterizer, and then have something where I'm able to test that on hardware and go back and forth. Maybe what I'll actually do is just again kind of rip everything out of the rasterizer and then just like add back features in the software module that I can test against the hardware module. Because I was also thinking that I think I mentioned a few streams ago that I wanted to treat everything as these sort of individual blocks of hardware, and then have each of those be individually tested and testable on the hardware itself, just in isolation, over for example UART, which is just the easiest interconnect that I've done. Maybe eventually I'll do Ethernet or something on my board, but right now UART's nice because it's supported by both my laptop and my PC, so probably run with that. But what I think I'll do is when I thought about implementing that, is my point. Then I also thought like I could implement, because when you test a module like that, you need to be able to send the hardware. It needs to contain your module and a little bit of stuff around it to process commands that you send to it in order to do those tests. And so I want to do that command processor also in this kind of language. And it'd be really nice to have all of that available as a software setup that I could sort of progressively build. And then a lot of that software setup should be reusable between modules, I'm hoping. And I just think that that's kind of the most natural way to build all of this, because then I can sort of make the command processor on its own and test it all in software. And then I know it's going to work. And then I build a Vivado project around that, which shouldn't contain that much code, or that much additional code. Probably a single top level module, which is probably also generated. That's what I'm hoping, but there might be others. So we'll see. And the nice thing is too, I might add some additional like custom components beyond just signals. For example, it would be nice to be able to describe RAMs and have those also in the model, as opposed to something right now I'd have to do that separately. So like something that acts like an SRAM with certain timing requirements or certain register delays would be really nice. Also, it's synchronizer chains would be another thing where it's pretty natural to describe. And the only real difference there is that you need to annotate some of the registers. So maybe that's how I implement it, is I expose some way to add those kind of annotations. I'm not entirely sure. But I think in the meantime, I just want to throw together some implementations of these binary operators, for example, just to get something easy out of the way and feel like I did something useful today, rather than just talked at all of you. Which I'm also happy to do, but you know. Hey, W Writer. Yeah, HDL, I should probably have said that. It's hardware descriptor language. That's all it is. So typical ones would include Verilog, VHDL. There's more of these meta HDLs, some people have called them. For example, Chisel is a really popular one. Clash is the Haskell one. And Migen, those are the Python ones. Or some of the Python ones. I'm sure there's a lot that I don't know about. But yeah, that's all that is. No worries. So was it bit XOR? That's the one that we want. So I'm just going to take bit OR and implement bit XOR, which I think should be really basic to do. I also need to have this here. So in this case, these are really easy because I've done 2 or more of these that are almost identical. So it's trivial to do this. The only real difference is here, because I need this bit XOR here. And so I'll add this here. And that will give me errors in the simulator code that references that. And then I also want to add some tests where I'm just going to copy this as well. Some of these just get really easy to do. And some of these are, of course, deeper because there's certain things where I haven't implemented everything I need. So these are also really easy cases because the two signals you come in and then the one signal you produce all have the same bit widths. If they don't, then they will panic, which is what these two tests are doing. Can't combine signals from different modules, and you also can't combine signals with different bit widths in this case. And I'm also enforcing those kind of things with like add, but like add, for example, will produce an output that is, you take the max of the input size, or in this case, if they're the same, you take the input size plus 1 bits is actually what the output should be. And then you need to do a bit more clever code gen stuff for that. In fact, I think I actually had some stuff on a branch that I should have stashed before doing this. Yep, I did. That's okay. We'll only add the stuff that I'm doing now. That's fine. Anyway, this becomes really easy, I think, because we had bit or here, and then we're just gonna map the module binops bit XOR to the simulator generators bit XOR, which doesn't exist, and we can fix that wherever that other error is. I think first of all here is where we want that, and then I think where it actually writes the expressions is the other place. And normally I would also need to implement this in the Verilog generator, but I'm not worrying about that yet. And the other thing that I want to do is I want to add these module tests like this. So again, I'm going to copy the bit or one. And we'll do this. And then we'll copy the tests as well. Okay, and then we need to do the actual truth table. So false, 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 true, false, true, false, true is true, true, true is false. And then I want to do something that will become true after this. We'll do true, false, and then true. Just some simple tests. So then if we do /test.sh, I think this will just work. So that's an easy one. And one of the reasons I also wanted to document this kind of, I want to say early on, but I did really design this API in Python before, so it's not that early. But one of the reasons I'm also documenting it now is because you get these tests in Rust where these documentation tests, and these are actually tested as part of your documentation generation, which is really, really nice. So that's what's basically happening when it says running doc tests, is it's actually testing all of this code. That's the documentation stuff, which is really cool. And I think the only other thing that I want to do is, I think maybe I didn't do for or and, but I like to have these bit width things tested as well. But I don't think we need it in this case. But yeah, it's really great if you're working on any kind of API in Rust. It's so nice to have that just tested as part of documentation that you should be writing anyway. Pretty cool. So yeah, so then basically most of any of the usage tests that I'm doing for these, for like the module creation, I do as doc tests. And then for errors, I do those as separate tests, just so I can use the should panic thing, make sure that we get the right error text as well. And then for testing the simulator, I rely purely on this generator package, which will generate one of those modules and then run its tests on the output. So I really like how all this is kind of integrated. And then also the simulator, having the simulator test like this also gives us a way to always test. That we have a nice way to test and demonstrate that we have a nice way to incorporate one of these generated modules in another Rust project, which I think is obviously the most important use case here. That, and of course generating Verilog, which is something that I still need to do for this implementation. But I have that one working in Python, so I'm not worried about it. I think I've said that several times now. Anyway, now we do this fancy add stuff because I don't want to add the other stuff I was working on. But this is basically trivial. That one is not what I want stage. Same with that. Oh no, I actually wanted to split one of those. Nice. Okay, that's one down. Now already these ones that end up always outputting 1 bit, those are not very difficult. It's add that where we kind of start getting into issues. And also these signed ones we need to handle somewhat specially, because then we need to make sure that this less than or equal to whatever converts its arguments into signed types before and then does the comparison. So we'll need to extend the code generator to handle that in those cases. Because a natural storage for just like a bag of bit symbols like this is just these unsigned values. And so I decided in the API to make these kind of things signed operators instead of explicitly signed operators instead of the other ones, or instead of like adding types to the signals, because it doesn't always make sense to have signed signals or unsigned signals. I think that's something that this level of abstraction shouldn't concern itself with, except that it needs to be able to expose ways to communicate to the simulator and the Verilog generator that we actually want to do those things signed or unsigned. So I'm putting those at the operator level rather than the data type level. But I think we could implement, for example, equality just as is, because I think as long as it returns the right output width, this stuff should just work. And in fact, one of the things I'm going to do here, I mentioned I had some of that code, some other code here that I wasn't too happy with. I think I'm actually just going to get rid of that. It was a first attempt at supporting add properly, but I think I'm just going to drop it. And we'll run the tests again, which is nice. What? Oh, no. Okay. This is one of the reasons I'm glad I haven't published this yet. Is because when I copied that, I copied some code on top of some changes that I had done. That's fine, because I can still force push to master in this case. It's here because we have source and target. I think this is just, in this current code, I think this is just bit width. In fact, I think actually none of these are here because it just takes the width from the input arguments. That's even simpler. Doesn't take too long to run this suite, although I think it uses a lot of CPU. So it probably makes my stream stutter. Oh well. What up? Yeah, the other thing also with these sine operators is in the simulator, we also have to generate the sine extensions for that. In the cases that the values that we're comparing don't have the same width as the data type that they're represented in the simulator, then we need to make sure that we sine extend all of the values potentially before we actually do the sine comparisons, which I don't think will be that bad. I think the way I would do that is I would do the cast first to get them in the right data type, and then I would just do shifts such that the top bit is actually the top bit, and then the shift down after that. You guys have seen me do that a lot in emulator code because it's an easy way to do that. Anyway, I think we can implement equality. Would be a good one to implement. So let's do that. Is that not where that is? Rust ops EQ SED CMP, that's what it is. Now, I think actually we want to implement either equality or partial equality. I've actually not really fully understood the difference here in Rust. So let's read some docs. Yeah, so this is a equivalence relation which has this transitive property. Actually, that's all these. Transitive, symmetric, and reflexive, which I think we will be able to satisfy all of these. So I think that's fine. And it also says EQ implies partial EQ and has no extra methods. So it seems like this is the one we implement, right? Errors on the code in my editor. Yeah, that is cool. That's just the regular, or is it Rust enhanced project, which I haven't updated in way too long. But yeah, it is quite nice. Sometimes it's not nice though. Like if you end up editing something that causes a bunch of errors on all these lines, then it blows up. But you can hit escape and then it'll interrupt it doing that, and they all go away. So that happens a lot too. Anyway, I think what I want to do is just implement EQ. But I think EQ has no extra methods. So the other thing I'm actually worried about here is that does this always return a bool, or can we override that? Because I want to override that. In the Python one, I actually decided for equality that I wouldn't do operator overloading, and then I just had a .eq or .ne methods on the signal, and that was fine. Maybe I do that here too. But I thought you could have these EQ and partial EQ. I thought that these could be, you could change their output type, but maybe you can't. This is just straight up partial EQ, I guess. Yes, these always output bools. So then this is not what we do. We don't use operators for this. I'm fine with that. Then we don't need to understand the difference. Although I think the other difference is just that would allow you to have for types that do not have a full equivalence relations. For example, floating point numbers, nan is not nan. Floating point types implement partially EQ but not EQ. Yeah, there you go, Medmuth. I think it's just that reflexive property. It seems to be that's the only one that this is actually missing. But yeah, we don't have to worry about that because we're just going to implement this as a function. And I'm totally okay with that. So in signal, here, then we'll have a method here. Bits, repeat, concats, etc. And we'll do pub fun EQ. I guess we'll do other for this. Cat should probably use RHS for this. I guess though, we'll actually call this RHS, looking at the code here. And then we are going to want to do some special stuff for the bit widths here with these bin ops, because I think this is now the first one in the current implementation where whenever we have a binary operator, the output bit width is different than the bit width of the inputs. So we're going to do that too. Bit width is U32. And that's going to give us a lot of compiler errors now, which is good. I'm also going to copy this here. And I don't think we're going to need any panics here. And or any other further stuff. Signal represents the Boolean. I think that's how I want to write that, which is great. So now we can do, let's create 3 literals here. A, B, and 3. Let's say we create, actually, let's just do 2 of these, and then we'll make these different. A and B. And then we can do to high, because we can do a dot eq lit a, and we can do, oops, not concat here, these should be eq, so b is equal to b, and then A is not equal to B, B is not equal to A. Basically trivial. And then the implementation of this should basically match one of these, but we don't have these panics here, so we don't need them. So LHS and RHS, actually we do panic in one case, don't we? 2 cases actually. If you try to combine signals from different modules, and if you try to combine signals with different bit widths, we should panic. So this is going to do the same ones as the other ones. And I think at some point I need to refactor this code to just have helper functions that check these two conditions. But for now, I don't really mind that it's duplicated, as long as it's tested. So we're okay here. Yeah, and of course now bit width. This is actually the first one where the bit width is different than the bit width of the operands. The other ones are going to have to be updated. So bit width is self.bitwidth on all these other ones. Okay, and then I also want to do some tests here. So we're just going to copy these same two tests here. And instead of bit and, we're going to call these EQ. And we're going to just do the same thing here. And that should do it for these tests. The last thing I want to do is, again, function bit width does a lot of these. I think in this case, I actually don't need to add another test for that in particular if I don't do it for the other bit ops, so maybe that's okay. Yeah, we'll leave it. And then I'll run the tests, which should, I think, pass. No, because we don't have this bit width field in here. We don't deal with that ever. This is one of the reasons why it's good to always enumerate all of these in cases where you need to know them. But I actually think do we need it here as well? Oh, also, a couple things that we need. This will not work, by the way, because it's going to have the wrong equivalence relation, which we'll see once we write the generated code test, so that'll be fun. I'm going to let it stay wrong until we prove that it actually is wrong. But yeah, we compile this, and actually, I don't think we need the bit width here. We want it to propagate the bit width to like other modules, but we don't need it here. And in fact, I actually do want to add a test for bit width for equality like this, because if we do or here, I want to do this, don't I? If we take m.lit u32 32-bit literal. Actually, we can make this an 8-bit literal. It doesn't really matter. As long as we compare this with another one, and I don't care about the result in this test, I just care that the bit width of this result is always 1. And now this should actually fail here. This doc test should fail. And it did, which is great. So now we can fix this, which in this case is just this. Instead of LHS, we want this to care about bit width. And we just return that. Now that should pass. Everything else passes too, including the sim tests. So I'm actually gonna sim. So for the simulator test, we need to actually add tests to test this. So what we can do is I'll just copy one of these bit or ones, for example, or bit and I think I put this after the concat tests. This. And then we need to also add this Oops, in the build script, yeah, because that was the test, but I also need to create the module. So you can take like bit and, I was putting it down here. EQ test module. Then we'll take bit and here. And we'll go down here. EQ test module. And we'll give it 2 inputs, and I want these to not be 1-bit signals. Make them 4 bits because that's nice and easy. And we do .eq. You can guess how I'm going to implement not equal that test. So here, do the same thing. I'll do 0xa and 0xb, for example. And then, is there an assert not equal in Rust? I mean, that is actually what we want. We want this to be equal to false, so that's actually quite okay. We'll do that. And we can also do a case where they are equal. And A should be equal. And what did I want to do here? I wanted to do this. 1 and 2, actually. Because here we could do, pick out some bit from there and some bit from here. Just so I get tested the single bit case as well. So these are 01 now, and then this last one will do I1 is equal to 0x. Actually, let's do this. Let's do a case where for when they're not equal, we can do 0 and, or we'll do 1 and 3, because then we can test that these are both equal in this case, and then we can test that in this case they're not equal, but for the single bit they are. And we can even do this. Sweet. I think that just works. And it didn't. That's funny, actually. And that's probably because the code generator is wrong, which is why we're testing this. Yeah, Moran, Happy New Year's. So 945 in modules, and this is one of the reasons why I spent a little effort to make the output readable. We can go find the error. And we can see what happened here is that temp2 is this and this. That seems wrong. And I think I know why. I think I mentioned this, actually. This actually makes perfect sense. That the module here, the implementation of EQ, I put bit and here, which is wrong. This should be equality, which of course doesn't exist yet. So we'll add it here. And now we're going to get issues with that's not covered in sim. So we'll start here. And module bin op EQ should go to bin op EQ. Of course, that doesn't exist yet. So we'll go down and add that. This kind of programming where you're doing these. I have equal here. I should make this consistent, shouldn't I? I'm going to do that. But yeah, this kind of programming where you're relying on unions like this is so nice in Rust. It's nice in functional languages as well for the same reason, at least the typed ones. So you can see in this case, I already have not equal in the simulator part of the compiler, but not in the module part of the compiler because I haven't exposed anything that does not equal. But I actually generate these not equal expressions in order to compare values against 0 in order to convert them to booleans. In Rust, I actually only learned this. You can cast from a boolean to another type, and you'll get 0 or 1 represented in that other type. But to go the other way, you want to compare against 0. So that's why I have that available to generate, but not expose to the user. So now that just worked. That was the issue. And so now you can see here, it generates this equivalence relation instead. So perfect. And of course that works for these U32s, and it will output the right type already, which is a Boolean. And we basically got that for free just by making sure that the bit width of the signal matched what we expect. And then of course that works in this 0 case. So here you can see it also, this is where the compiler will generate, because ultimately it needs to generate this equivalence relation here. And it does those from getting those bit values, and those bit values need to be cast to Booleans. So to get those values, it takes these inputs and ANDs those with 1, and then it will compare those to 0 to get the actual Booleans, which is 4 and 6 here, and then that's what's actually compared at the end. So this is beautiful code here. And yeah, again, I very liberally create all these temp values, but that's how we get this code to not explode in pathological cases. Because before I would just have it output whatever the node was more directly, and then you end up with a lot of cases where instead of looking like this, you end up with this ends up being whatever temp 5 was. So you end up with like self.i1 and 1 and then here you have not equal to 0 is equal to the other one. And this is not bad in cases like this. In fact, this might even be preferred in simple cases like this, but these explode quite a bit. And if you do something that ends up in this kind of expression, and then you have repeated it, it will end up repeating this over and over again. If you end up with something like this, just because you referenced bit 0 of this other signal several times or had that being repeated. So at least in those cases, you kind of need to generate temporaries. And I just decided it made more sense to pretty much always generate temporaries. Because then we never have those pathological cases, even though it makes code like this a bit longer, but I think that's fine. And then of course the Rust compiler is going to handle this really well, and it's nice. So I think that's about it, other than running cargo format. Do that on both of these, even though I don't expect anything to really have changed from that. And I'll run the tests one more time. And the only reason I have this test.sh script again is to it just CDs into both of the directories of the two projects here and test those one by one. So it's just convenience for me. But yeah, that works. I trust this enough already. This is such basic code that I'm not even worried about that. So I will of course look at the diff though again, but it should just be, there's our test module being generated and tested. I'm really pleased with this, by the way. I don't know if I mentioned that, but I actually love that I ended up doing this simulator and porting this HDL to Rust. I'm quite pleased. And eventually I will properly announce this when I actually publish it, which hopefully won't be in the very distant future. I think there will be some other people, especially in like the games tech Slack, that are going to be interested in seeing that. This looks good. I don't see any stupid errors, at least. And then test documents signal EQ. We don't use loading here because in Rust EQ, partial EQ always return bool, whereas we need to return a signal. Okay. And that's equality, and then we'll do inequality as well, because that should be really easy to do now. So we do the same thing. We are going to copy and paste this and invert everything and call these NE, except this one actually should not have changed. That's funny. And here we'll do NE and that. And I think, yeah, I like that these are consistent. So yep. And this should be not equal, which then we'll add. It's actually enum put up. And I need to, since these are public, at some point I need to document all this stuff as well, but I'm not that worried about it at the moment. And then we need some of these, which we will just do copy and paste again. And E. And then in function bit width again, I want to do the same thing for NE as well. Okay. I think we're not good yet because we need to implement that in the compiler and everything too. So I'll just go ahead and do all of this because this is so similar. Okay, and then we'll go up here and make sure we have that created. And then the test, we'll just test here. And let's instantiate the right one. And so here, of course, these are not equal, so these are both going to be false. And then when we set these, then I think this becomes true because they are not equal, and then false because those ones are equal. Great. And then the simulator, we need to handle, I think all we need to do actually is this, just handle this particular operator mapping. And I think everything else exists, so I think we're okay there. And then we test. Now I know that I like this API because I've already used it in the Xenowing project for, or at least the Python implementation. I was already quite happy with that for some of those things, even though it didn't have instantiation yet, which is something that we eventually need, of course. But format, just to make sure. Run test again. But the real test is of course when I start implementing more complex modules and getting more tests simulated and everything. Now I think this will work out for the better. At least I'm gonna enjoy using this, but you never quite know when you're building a tool like this. So maybe I ended up hating it too. I always think that's kind of a fun gamble when you do compiler-y things. Okay. What else do we want to do? So for less than and greater than, I also want to see if we can change those. I don't think we'll be able to. If we can change the output type, that is. Oh, did those use ordering instead? They might. Yeah, I think they do. Just looking at the list of available operators to overload. Rather, you do actually... No, there are actually ordering traits, for example. There's partial ord and ord. Yeah, so like LT always returns a bool. So we're also going to end up doing LT and those kind of things not as operators, which I'm perfectly fine with. It'll make them the names more consistent with like LT signed as well, so it doesn't really matter. You know what? I think I might be lazy and stop streaming today. And then handle these in a bulk later, seeing as I've already been streaming for a couple hours. Yeah, I think I'm gonna do that. I think I'm gonna call it good for today. I got to talk a lot about this project today earlier, so I'm happy about that at least. Anyway, thanks guys for hanging out. I hope to make some good progress on the rasterizer in the next couple weeks once this is all ready to go. And I'm quite confident that I'll be able to come up with a good macro solution for those conditionals and everything. So should work out quite well. We'll see. Anyway, thanks again for hanging out, and I'll see you guys later.